Good afternoon. On behalf of Oxford University Press Pakistan, I, Seema Khalid, would like to welcome you all to the first webinar week of Oxford University Press. The title of today's webinar is Problem Solving in Mathematics. The session will be facilitated by Michael Pearson. Michael Pearson is a UK qualified teacher originally from Manchester, UK, who has lived in Pakistan since 2007. He has taught science and mathematics for over 25 years and has been a school leader and teacher trainer in the UK, Qatar, and Pakistan.
Good afternoon, everyone, and welcome. I'm really pleased to be able to be here this afternoon sharing with you, and hopefully we'll learn something together over the next hour or so. So let's get going. There we go. So the following slide, you're going to see three famous mathematicians who I'm going to introduce you to. And what I want you to think about is if they were alive and living today and they were going to write a tweet about something that was going on in mathematics or just life in general, what would that tweet be? And you're going to write the tweet in the chat box, and then Seema will read out a few of them for us as we go along. So let's have a look at these three mathematicians. First one takes very little introduction. That's a picture of Pythagoras, and I think anyone who's taught maths at any level will have heard of Pythagoras. He was born on the island of Samos in the 6th century before Common Era, and of course came up with his most famous theorem of the square on the hypotenuse is equal to the sum of the square of the other two sides. This gentleman, not many people may not be as aware of. His name is Omar Khayyam. He is one of many Arabic mathematicians. Maths came to a bit of a stall in the Greek world because they had no concept of zero, and it took thinkers from outside of the Greek world to move mathematics on, and Omar Khayyam was one of those. He is probably best known for his work on cubic functions and graphing and mapping those. So that's Omar Khayyam. The last painting here is of a lady called Ada Lovelace, and Ada was involved with the Charles Babbage difference engine, which of course you will all be aware of was the forerunner of the computer. And it's through her work, along with Charles Babbage, that we're able to do what we're doing today. Had they not done the work that they've done, we wouldn't have the modern computer. So for a minute or so, have a think. You're going to write a tweet from one of these people, either about mathematics today or just the state of the world. What do you think one of these people would have to say? I'm going to give you a minute or so to write your ideas into the chat box.
So Michael, we have some responses.
Go on then, while I get the screen up to date.
One person has written what was common was calculation.
Okay, definitely. There was lots of calculations that needed to be done. Go on, anything else?
Other person said that they loved maths and problem solving.
Ah, definitely. Yes, there was definitely a love for maths.
Someone is saying that they started with assumptions and ended with a rule.
Ah, good. I like that. We'll come back to that in a couple of minutes. They started with an assumption and came up with a rule. Brilliant. What else?
Critical thinking and logical thinking.
Yep, definitely. Even before it was trendy, people were doing it.
They modeled the mathematical problems, is what someone is saying.
Absolutely. Any more?
That's about it.
Brilliant. Well, I'm glad somebody else came up with this, but the way I framed it and phrased it is that the common element was that they didn't have the answer. They only had a problem to which they had to come up with an answer. And it's very different often to the way that we teach mathematics these days. Too much of our teaching is rooted in, here is the problem, here is the answer, get on and learn it, without any real understanding of what lies behind. And that's a real issue for us, because it means that children are not being taught those critical thinking skills, those logical thinking skills, those problem solving skills, which will help them move on to the next phase. If Omar Khayyam had just sat there with his Pythagorean maths and thought, oh, that was lovely, I've learned it, and now I can find the length of the hypotenuse of a right angled triangle, and not gone further, then mathematics would not have developed in that area of algebra. If Ada Lovelace had been happy just to sit there and go, Mr. Babbage has done a nice job with that difference engine, but she saw a problem which she then had to solve. We need to be talking in those terms with our students when we're teaching mathematics. And it's hard, I accept that. I've been a teacher for nearly 30 years, and we're often being pushed by the exam, by the syllabus, by the expectations of the students and the parents. But if we're going to be good at what we do, and if we're going to help them to be better mathematicians in the future, we need to be giving them that idea that problem solving is important. We don't often ask them to think how, we just ask them to find the answer. And that is clear, and it starts right at the beginning. And maybe we need to make sure that this message gets down to the little ones as well as the big ones, because we need to start right from the beginning. I don't know what age group you teach, but if you're teaching the young ones, you need to make them inquisitive about what's going on in maths rather than just teaching them facts. Being a mathematical thinker and a problem solver leads to success. If you want your children to be good at maths, they've got to think mathematically, they've got to be problem solvers. They have to have a conceptual understanding of what's going on. Many people can do certain things in maths, but they don't understand why. If they're going to move on to the next phase to be better mathematicians, if they're going to help develop the world into the next phase, then they need to understand why. They need to be aware of how numbers relate to real concrete materials and the events in the world. Numbers are not just abstract concepts, they are, but there's more than that, and the mathematics has to relate to what's going on around them, finding real world examples to solve real problems. And they've got to be flexible. They've got to go beyond replicating procedures. Yes, it's important that they can solve a quadratic equation using the formula. Don't get me wrong about that. They need to practice that, and they need to be proficient with that. But they've got to be able to go on from that and think, well, how can this be applied? Somebody said at the beginning, you know, another day has gone by when I've not used Pythagoras' theorem. And a lot of kids feel like that. Why am I learning this? It doesn't help me. When am I ever going to use this? We have to make things real and concrete and related to what's going on in life. It's also a life skill. Being able to solve problems, you know, we're faced with problems all the time. We've just had the 10 minutes of problem solving to try and make sure that you can see me and can see my slides. It means I'm now running 2 laptops here, and various people have been running around. But it means that we need to have a problem solving approach to life, and that's taught to our students, and maths is a good place to do that. But there are other related skills that they need to have. So again, into the chat box, if you can you type in things that are other related skills that will contribute to a successful mathematician? So finding patterns, yes, absolutely. I can see the chat box now, Seema, because of the way the computers are set up in here, so I can read what's going on. So Aisha has said that finding patterns, and that's hugely important. And it is something that we teach to little ones, and we forget about it as we get older. But maths is all about patterns. It's about being able to replicate things. What else? What other skills are necessary to help develop a good mathematician? Anyone else? One thing I would say is they need to know certain facts. Sometimes we go one way or the other. And so there was a move in the UK when I was training as a teacher to new maths and all of this problem solving and whatever. And we forgot about knowing facts. We need to know our times tables, for instance. We need to be confident with those, because so many other areas of maths depend on the fact that knowing that 7 8s are 56 rather than and counting them off on our fingers. How do we know? How are we going to do fractions well if we don't know our tables? How are we then going to do probability well if we don't know our fractions and we don't know our tables? We need to, yes, Aisha's made another comment. We need to work smart, then work hard. The two things go together. It's not just about working hard, and that's what students don't always understand. How are you going to improve in this area? I'm going to work harder. what does that mean? And they struggle to understand what to do. And that's another life skill that we need to teach them. And that's problem solving again. How do I solve the problem? I'm not doing very well in maths. How do I make it better? So just a quick plug for some of our books. One of our most popular books is the new Syllabus Mathematics, and many schools in Pakistan use this textbook. And so it doesn't really need much of an introduction to you, but there are 4 textbooks, and it's based on the Singaporean approach to mathematics teaching. But we do use it a lot here in this country. And the textbooks are backed up by workbooks, and those workbooks are backed up with the teacher's resource books as well. So the facilities are there, or the resources are there and available from OUP, but they're working towards this problem solving idea. You see, the Singaporean idea for mathematics teaching is based on a problem solving curriculum, but there is also an emphasis on the development of intellectual competence, such as the ability to visualize. What many people struggle with is actually seeing what's going on in mathematics, and it just becomes a set of operations that they do. But if they can visualize what's going on and see what's going on, that will help them to understand. And it's the understanding that we need. Some people have that innately. You've all taught people, I'm sure, where you've thought, this child just seems to understand. But those are the exceptional ones. There are many who can be taught that as well. It's not just about, oh, aren't I lucky I've got an exceptionally gifted person who just sees it. It's like music. There are some musicians who can just sit at a piano and play and never really have to be taught anything. It's just innate. But you can also become a very competent concert pianist through lots of hard work and practice. And that's true with maths as well. It's not just, oh, I'm good at maths, I'm bad at maths. You can teach maths, but there has to be an emphasis on conceptual understanding. It's got to go beyond the nuts and bolts of just knowing what to do. They have to understand why they are doing it. They have to have mastery over what they're doing. And we're going to talk about mastery in a little while and why that's so important, and the 3 stages that a student goes through until they've mastered a topic. But if they're going to be problem solvers, if they're going to be able to look at a situation and think, right, what do I need to do here? They need to have mastery over the maths that they already know. And we have to be systematic in what we do. We need to develop skills and concepts. The students need to understand what they're doing and why they are doing it. And we'll come on to that in a few moments' time. So on the left-hand side there, you've got those things that I've just emphasized from the Singaporean. There's one more come on to the bottom of there. They have an emphasis on this concrete, pictorial and abstract approach at the primary level, but I'm not going to talk about that very much. I meant to delete that, so apologies for that, because that's more at a primary level and I'm a secondary school teacher. But what I want you to do for a couple of minutes is just to think about how you teach maths, or how maths is taught in your school, and how does that compare to what I've just been talking about? Do you have problem solving as part of your curriculum? Do you emphasize the development of intellectual competency and an ability to visualize? Do you emphasize conceptual understanding? And are you systematic in the way that you teach skills and concepts? So have a think about that for a minute or two. And if you want to say something, just type it into the chat box and then I'll say it out for everybody to hear. See, the advantage of doing this in the real world is that you can pick on people. You can go up to their table and thrust the microphone into their faces. That's much harder when you're all scattered around the country. So if you don't talk to me, I will have to carry on talking on my own. I suppose as an outsider, and I have been in Pakistan for 13 years, but I'm still a bit of an outsider. My observation is that sometimes maths is not taught in that way. And even as someone who's trained in the UK and worked in the UK, sometimes I don't teach maths that way because it's easier just to say, oh, just do this. You don't understand, you don't need to understand why, just do it. This is how you solve quadratic equations with the formula. Plug this in here, this in here, this in here. It's easier. The way we're talking about teaching now requires a lot more effort on our part. And that's hard to do with all the constraints of what's going on in a school in normal situation, and everything we're facing at the moment is even more abnormal. But it is important that we try to make sure that the majority of our lessons are based around concepts and around understanding rather than just doing. You know, the worst examples I see in some systems is where they just learn an answer and then regurgitate and repeat, excuse me, in an exam. And that does go on in some systems of education, and they're then unable to apply something. So back to Pythagoras, I was told once by a teacher somewhere that, you know, in the exam they would be expected to know that the triangle that has a hypotenuse of 5, you can then calculate the other two sides as being 3 and 4. But if you gave them a triangle that had one side as 5 and one side as 12, they wouldn't be able to work out the length of the hypotenuse as being 13 because that was not in the syllabus. And so what they actually did is they just learned set questions, waited for those questions to turn up in the exam, and gave out the official answer without any understanding whatsoever of what they were doing. That's not what we're looking for. That's not going to create people who can then problem solve and can think and can move on. So if we look at this diagram, here's again an idea of how we can build up our curriculum. Okay, at the very foundation, if we look at that, it's like a house, it's a pentagon, but if you look at it as a house with the concepts as the floor, progress and skills as the wall, and then attitudes and metacognition as the roof, you can't get the roof up until the floor is sorted and the walls are up, and then the roof goes on. So it's all based and all focused on the foundations of the concepts. And those concepts that need to be numerical, algebraical, geometrical, the probability stuff, and then being analytical and also being statistical. All those areas of maths that as teachers we are used to teaching. But as children, the students need to understand the concepts that lie behind them. If we're going to build a strong and secure house, you've got to have good foundations. What we often end up with is fairly shoddy foundations and then some rickety walls and maybe a bit of a roof going on, sufficient for them to pass through their metric or through their O-level or IGCSE, but they don't really fully understand what they're doing. And that's why people then don't go on and study maths further. If we work hard on the concepts, we can then, on the sides of it, look at the skills and the processes. And they're there for you to see the different ideas of which skills and which processes the students need to do. Once the walls are firmly established, then you can pop the roof on, and that's when people take off. That's when they move, their attitudes are brought in, and attitudes are important. Remember what I said earlier on, the Greeks came to a grinding halt in mathematics because they could not get a concept of zero. And that was partly to do with their religious beliefs at the time. So their attitudes, their beliefs, influenced their ability to move on in mathematics. And it was only when other thinkers came along who had different religious beliefs, whether those be Christian or Muslim, and they were able to accept the concept of zero, that's when mathematics moved on further. So don't rule out attitudes, don't rule out beliefs, because they are a very integral part of how we move on intellectually. If we can get stuck in a certain set of beliefs or interests, or our confidence can be shaken, and it will mean that we don't move on. And then this idea of metacognition, being able to monitor your own thinking and to be able to regulate your own learning. If only I had a chemistry lesson today with my year 10s over Zoom, and I kept saying to them, you need to tell me what you don't understand. You need to regulate your own learning, basically. But what we often create are passive kids who sit there and just want it to be told to them. If they're ever really going to understand their chemistry and move on, they have to look at it and go, right, I know how to work out the number of moles, but I don't know how to work out concentration. or I can balance those simple equations, but I can't balance these more complex equations. And that's what we were talking about in my lesson this afternoon when I was meeting with my year 10s. That's what we need to get across. That's what's got to be clear in our teaching, that's what we're aiming for. But it builds up just like a house, and it starts with the concepts, then the skills and processes, then the attitudes and the metacognition. Often we focus on skills and processes, miss out the concepts, and therefore we can't move on to build up the roof. So I mentioned this idea of mastery before, and this leads into problem solving, because students have to have mastery of certain skills before they can then look at a problem. So the most important thing is that all pupils can succeed. They won't all succeed to the same level. That's clear, and there's no point pretending that we will all be, Ada Lovelaces or Uma Khayyams. We're not all going to create new maths, but all pupils can succeed. The danger is we often write people off. People are frightened of maths. Oh, what? You meet somebody, what do you, oh, I'm a maths teacher, oh, I hated maths. How many conversations have you had like that? That can be a problem, but if we go into our classes with this idea that everybody can succeed, it will be good. We have to have problem solving at the heart of learning to help them to understand and to gain mastery over different topics. They've got to see that this is the answer to a problem, because that's how it was first worked out. Pythagoras will have had a problem where he needed to do that. Thought, right, well, how do I work? And he tried different routes. Charles Babbage and Ada Lovelace will have gone through hundreds and thousands probably of prototypes until they got the difference engine working. And how much research and development has gone on between their day and now, which means I can sit here in Karachi talking to all of you wherever you are in the country and the world. That's all been done by problem solving. We need to be consistent in the use of concrete models and pictures alongside abstract. Way back when I was teacher training, I learned about Piaget's different stages of understanding, and we need to be aware of that at times we need to be concrete, that actually what a child needs to be able to do is go 1, 2, 3, 4, 5. But we've got to move away from that. We need to move away and help them to move on to a point where they can just imagine what 5 looks like. They don't need 5 fingers or 5 bricks on the table. We need to move them on to that deeper understanding so that they can explain concepts to you and show that they understand what they're talking about. And we need to vary how we teach. It's so much easier to stand at the board, write examples on the board, copy them down, write more examples on the board, copy them down, write more examples on the board, copy them down. That's easy for us and for them. But if we can create a variety of teaching activities and bring different aspects of different skills and different ways of learning into the classroom, we're going to really help the students to move on. And we need to be precise. This is one of my biggest bugbears, precision in mathematical language. We have to use the correct terminology from the beginning. And unfortunately, when you're teaching in secondary like I am, you are inheriting all sorts of misinformation from primary. And that's often because mathematicians don't teach in a primary school. And so the people teaching know things, but they don't know the right words. And so we have to be clear and we have to say that this is what we mean. And there are so many examples that come out of people using wrong language. And, and again, sometimes it may be different culture, but people here will say, 4 into 5 equals 20. Well, where I come from, into is a slang word for divide rather than multiply. Much better, so there is no confusion, we use add, subtract, multiply and divide. So if we use those words right from the beginning, it would help students to get their concepts clear. But we don't, we use shared, we use times. If we're teaching 4 and 5-year-olds new words and new concepts, use the right maths from the beginning. Use the right words from the beginning. Don't call it an oblong, it's a rectangle, because an oblong is not, all rectangles are oblongs, but not all oblongs are rectangles. And that's not even true, because a square is a rectangle and a square is not an oblong. So don't use easy words, teach them the correct word from the beginning. I could go on for that for hours, but I won't, because it's not really what we're on about. But it is important to help them with their understanding. So what do I mean when we use this word mastery? Students who show mastery in a particular topic or aspect of mathematics are able to solve problems because they have knowledge of that, how, and why related to the topics. They have factual knowledge, so they have the knowledge that, they have procedural fluency, the knowledge of how to do something, and the conceptual understanding of why. So what does that mean? Let me give you an example. So we're talking about angles in a triangle. If we can say that our student has mastery of that topic or that aspect of the topic, they know that the angles in a triangle add up to 180 degrees. They know how to work out the angles in an isosceles triangle given one of its angles. So they know, not only know the fact, but they know how to apply that fact. So you give them an isosceles triangle and you say, right, that angle there is so many degrees, what are the other two angles? And they know why the angles in a triangle add up to 180 degrees. So they know that, they know how, and they know why. Another example might be a student in class 6. You say to them, what's the total cost of buying 12 apples, each costing 23 pence? That's because this was a UK example. Let's say 23 rupees. So we're saying it's 23 rupees. And they sit there and they go, well, that's 23 at 23 at 23 at 23, 23 at 23. And they go through it, they go through all the agony of that and say, it's 276. That's the correct answer, but they haven't shown mastery of that particular skill. Because what they need to be able to do is move on. They know that the total cost means that you add all the prices together. That's fine. They know how to do that. They've got a procedure for finding a total, but they have not yet reached that why of understanding that actually we can skip that and say that actually if we've got 12 items that are the same price, we can multiply rather than repeat add. And that's the difference. Once they've got that, once they've made that conceptual leap to think, adding the same number a number of times is the same as multiplying by that number, then they have mastery over that subject. All right, so that's what we're meaning. And once a child has mastery over a variety of topics, that will help them in their problem solving. They will be able to move forward because they will look at the situation, all right, I need to do this here, or to move on, we need to do that. But if they don't have that basic mastery of different skills, then they're not going to see that and not be able to move on. So how do we teach for this? Well, over time, if we're teaching towards mastery, it embeds in pupils a secure, confident, flexible. So secure, confident, and flexible. So they know what they know it, they're confident about it, but they can also bend around it. They've not learned it in just one line. They can weave around and go, right, okay, that can apply here, that can apply here. That crossover of knowledge from one topic to another. So an example might be that they are confident and secure with how fractions are added, and they can then move that over to the study of probability. Sometimes they'll sit there with a problem that is all about fractions and be able to do it, but then when you ask them to do it in a different context, they can't. That means they haven't mastered that particular skill, and they need to be fluent with that, and they need procedural fluency and conceptual understanding. They need to know why, and they need to be able to carry out a certain task easily. You've all stood there, I'm sure, with students who are labouring over something, thinking it's not that difficult, just get on it, but they haven't reached that procedural fluency. And when we're using the word mastery or its associated words, we're always talking about these things. And we always use mastery to refer to the student. It is the student who has mastered something. It's through what we do as teachers. We are the one facilitating and helping them to move on, but they are the ones that gain mastery. Mastery describes the outcome and not the process. There are lots of different ways of helping a student to master a topic, but it's the student who masters it. We are the ones that facilitate that and help them to get to that mastery. So those 3 steps can be applied to any particular topic. So they need to have that knowledge of the factual understanding. They need to be able to know that that is the piece of knowledge that we're using. They need to know how to do that, have procedural fluency, and they need to know why. So I've been talking for quite some time, and we're coming towards the end of my talking time, and I just wanted to give you a chance to think about something. Think about the topic of trigonometry. If you were going to make lists under the that, how, and why, picking some aspect of trigonometry, what would those be? If you're willing to share your ideas in the chat box, you can do, but I'm going to give you just a couple of minutes to think about that before I sum up, and then we go over to questions. So thinking about trigonometry, make a list under each of the headings of the things that students need to know or be able to do to have mastery of that topic. What comes under the that? What is it that they need to know? Which procedures do they need to be able to be fluent with? And which concept do they need to understand? So has anybody got any ideas that they want to share with us? I'll let you think about that and work on it because I'm conscious of time passing and we're coming up to the 4:45 point, which is going to be the point where we go over to questions. But some of the things that I've thought about in terms of factual understanding, obviously they need to know the ratios. They need to know that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent, and on we go. They need to be able to use those fluently in finding unknown angles and unknown sides. And they need to understand why that happens. So they need to have an understanding of how the sine graph works and how the cosine graph works and why those things are related to one another. And we can go on and through each topic we wanted to look at and think about those things. That's probably an activity that's better done when we're together, if I'm honest. So one thing you can do if you want to find out more about problem solving in maths is get registered on Oxford OWL, because there are lots of free resources there for problem solving within mathematics, and which will give you some ideas at different levels, primary and secondary, but things can be adapted. And don't rule things out for the secondary department. Sometimes we think, oh, now we're in secondary, we have to just have a pencil and a piece of paper. Sometimes actually doing some activities might be what they need to help them understand better and be able to move on. So I'm going to stop talking at you now because we're at 1:45 and I was given 45 minutes, which I've used. Do you have any questions? If you just type them into the box and I will do my very best to answer them.
Hi, Michael.
Yes, Seema, take over.
All right, so I'm going to ask the questions that have been published. And before I ask the questions, I just want to make an announcement that in the chat box, you can find the link to mark your attendance. And only the ones who will click on the link and submit all their details will be able to receive a certificate. I can see that there are only 281 hits on it. So if you have not filled that a link, please do so. So Michael, the first question that is very popular is, what do you think is the best technique of problem solving, heuristic or metacognitive?
the best way is always to try and be as practical as you can. I think that's the thing. It is about what we've been talking about in terms of getting them to be confident with various skills, but then to apply those. So if you are going to teach trigonometry, teach them the basics of it, but then give them a problem. It might be, how tall is the barrier tower? You know, and then if you can get them out to do that, or if you've got a tall building on your campus or near to your school, say, well, how tall is that building? And that can be your starting point. So we need to find the height of that building over there. That's the practical application for most people in trigonometry. It's been included in the syllabus for years and years and years because it's also a method of navigation. But most people don't need to navigate on the seas anymore or by air in the air. But you can use it to find the heights of tall buildings. That's what quantity surveyors use when they're measuring the heights of things. So start off with a real world situation and say, if we needed to find the height of the barrier tower on the seafront in Karachi, what do we need to know? How are we going to do that? Well, we would need to know this and this and this, and then show them how to use that.
All right, thank you, Michael. The next question is why algebra is so interesting in the beginning, but then with the passage of time, it becomes very confusing and boring.
Yes, you're right, it can do. I think it's because of the slog that's involved and the way that we've all been taught it. Often it is taught as very, you know, it does become dull because it's taught in a dull way. Mathematics often leads into philosophy. In many universities, mathematics leads into philosophy and about thinking about the big things about life because it's such an abstract topic. And what we need to do is we need to think about more ways of making it real to people, right? I don't know whether you can still hear me, can you?
We can hear you, Michael.
Oh, that's all right, because the lights all went off, so that's fine. So we need to think about real ways of making algebra fun. And it can just be about playing silly games with it. I've used equations in the past to find a way through a maze. And getting them to do it to try and achieve something like that, they will do an awful lot. I haven't got the example on me at the moment, but you can use it to create patterns, you can do whatever, and get them to, the one that I've used quite a lot is where you're expanding brackets, for instance. That's what it was. And you give them a grid, and I think it's 10 by 10, and they have to find a path across the grid by finding the correct ones. Now, if you gave them 100 examples in an exercise book and say, right, expand all of these brackets, it would take them forever. But if you give them the challenge of getting from one side of the grid to the other side of the grid by finding the correct ones, they'll do it in less than 40 minutes. And they won't do all 100 of them, but they'll do enough of them to practice expanding the brackets. And we need to do that with other things as well. And that's what I was saying before. By the time we get into year 10, year 11, into A level, or it becomes very dull. We need to find ways of making it exciting and interesting. And sometimes it's as easy as giving them a game to play where they have to do algebra to move on in the game. And when they've got an aim like that, they're willing to do it because there is a problem to be solved. It's not something brand new. They're not going into a new area of maths, but they've got to get across the fiery canyon or whatever it is by solving maths problems. And it will increase the interest and increase the excitement for maths.
All right, next question, Michael.
Yeah.
And this is a question which is very relevant to students in Pakistan. Language barrier makes it very difficult for our students to comprehend questions. What can we do to make this better for the students? How can children better comprehend math questions?
You have to teach in the target language. That's the key. And what happens too often is, and I see it in my own schools as well sometimes, is because we do O-level and IGCSE, all our examinations are done in English. Most other exams are done in English as well. But if you teach them in Urdu, then they're not going to be able to answer the questions. And it has to be done from the beginning. And that's what I was saying about not using slang words for different procedures in maths. Talk about addition, subtraction, multiplication, and division right from the beginning. Children will absorb these new words. They're learning new words all the time. You don't need to make it easy by saying share or times or any other of these words that we use lower down. But all the teaching has to be in the language that the exam is being sat in. So if your students are taking maths exams in English, then you have to teach in English all the time so that they become confident with those words. If you keep translating back into Urdu for them, or Sindhi, or whatever it is, wherever you are in the Punjabi, wherever you are in the country, then they are going to fall down because they're not going to be used to sentences. And you need to spend time going through the questions as well. That's what I do with my students. I'll sit with them and say, right, we're not going to worry about solving this at the moment. I want you to understand what the question is asking. And that's hard even when people's first language was English. I remember as a student when I was a teenager struggling to understand sometimes what the question actually wanted me to do. And it's only once you learn those command words, for one, and know your mathematical words that you can then actually understand the question. So it's about teaching in the language the exam is being taken in. That's key. But also then going through and dissecting the paper and dissecting the question, saying describe means this, explain means this, calculate means this, work out. And some of them fall down on that. Calculate the answer to, and they go, but I haven't got a calculator. But calculate just means work out. And so you need to spend time in your lessons training them on what the command words mean.
All right. Next question is, what is the simplest strategy that you would suggest to help students in doing problem solving?
Practice. They've got to practice it. So you've got to give them the opportunity to do it. And when you first do it with them, when they're younger, you need to walk them through it. So say, right, we're going to do this all together. So you can put a problem up on the board, up on the screen, however you're presenting to your kids, and work on it together and show them step by step how we can solve that particular problem. And then let them do the first part, then let them do the first two parts, and build up to it slowly. But it's about practice. All of maths is about practice. If we're going to get mastery over any topic or any subject, we need practice. It's not something we can do once or twice and then we know how to do it. Maths is a skill. It's just like playing the piano, riding a bike, playing hockey, playing cricket. You know, our great cricket players of the past didn't just walk up to the scene one time, whack a couple of balls and go, yeah, right, I'm right now ready to play for the national team. They spend hours and days and months and years practicing. And even when they're in the top flight, they carry on practicing. You know, a concert pianist doesn't get to the top of his or her field and then go, oh, well, I'm okay now. They'll still spend hours practicing. Maths is the same. If we're going to get that mastery and be able to solve problems, we have to practice it. But we need to scaffold and build them up to it. We can't just throw them into the deep end and hope that they'll swim, because most of them will drown and that will turn them off. Whereas if we set up and say, right, this is a problem, right, what's the first step? Well, my first step would be to do this. And then we go like that. And if we build up to it slowly and take them through it and do it regularly, then they will get the idea of what to do.
All right, Michael, next question, which is in the chat box, but I cannot find it. I'm just going to announce it. I haven't published it, but that is regarding the use of calculators. What do you think is the right time to give a student a calculator in hand?
The right time to give a student a calculator is after they've mastered estimation. They have to know that the answer they've got is reasonable. And I bang on about this with my math students all the time. Is your answer reasonable? And once they know how to look at an answer and go, yeah, that's reasonable, then they can have a calculator. If you introduce a calculator too early, they become slaves to the calculator. Well, this is what the calculator said. Yes, but like all computing devices, it's garbage in, garbage out. If you put the wrong information in, then the calculator will just tell you what you've asked it to do. So if they don't understand how to put a question into the calculator, and they don't understand whether or not the answer they're getting is reasonable, then there's no use to them. So a simple example would be, you've got 570 students and each bus will take 30 students. How many buses do you need? And the answer comes back 4,390. That can't be right. But that's what the calculator says is what the student says to you, because they've done the wrong operation. But what they haven't got is that notion to look at it and go, that's not right. Whereas I'm doing things on the board and sometimes I'll suddenly stop and go, no, that's not right. And the kids will look at me and go, that can't possibly be the answer. I've done something wrong because that answer can't be right. I've got the probability to be 1.7. Well, I know that it can't be more than 1. So I've done something wrong. So once the kids have that notion of being able to estimate and look at an answer and go, okay, that's not reasonable, then they can use a calculator to assist them.
All right, I think we have time for 2 more questions. So this would be the second last one. The question is, what is the purpose of theorems and how do we make it interesting?
Sometimes you can't. Sometimes you have to say to the kids, you have to learn this. And the purpose of theorems is to give them the information so that they can solve the problem. So circle theorems are dull, but if they know them all, then when they look at a problem, they can get involved in the problem and go, right, well, which one do I need to get? Right, I've got an angle here. Oh, right, that's on the circumference. That's a diameter. Oh, right, I know that that's a 90-degree there. But if they don't know the theorems, they haven't got a hope of being able to answer a particular question. And so I do say to my kids from time to time, you need to learn this. You need to know that the sine equals the opposite over the hypotenuse. Until they know that theorem, that fact, then they can't move on in trigonometry. And the same is true when you're solving problems with circles. Until you know the 7, 8, 10 theorems that are currently in use at O level and at metric level, until you know those, you've got no chance of solving the problems. So we have to be honest sometimes and say, right, guys, this is going to be boring, but you need to learn this. Once you've learned it, then we can have some fun. And I enjoy circle problems because you sometimes just have to think about, which one is it? What am I looking for? Ah, there it is. Ah, ha, ha, right. We've got 2 tangents, right? And that's, if you watch it when we're doing circle questions, that's often how I am. If they go, so I can't do this one, so I draw it up on the board and go, right, well, what? Ah, two tangents. What does that mean? And you can help them with that. And then that's when you can get excited about it. You can turn it into a challenge with them rather than just a slog of going through questions. Excuse me.
All right, Michael, this will be the last question.
Okay.
And teacher is asking, I suppose this teacher is teaching at a higher grade, 9 or 10, because this relates to students who go for external exams. So she's asking basically that there are lots of students who are doing advanced concepts in mathematics, but they make these mistakes at points where the problem solving is very basic, like you have to just calculate basic tables or you have to look into place value, and that's where the problem occurs. They don't get it right, which is why the solution and the answer does not come right. So how to teach those basic things at the advanced level?
It's practice, and I cannot multiply 2 numbers together and get the right answer, gentlemen, ladies. What's going on here? And it's because they become lazy with certain things like that, and partly because they rely on calculators. So you'll say to them and say, what's the angle here? And they're reaching for their calculator, saying, you can't do 90 minus 45 in your head. So they become lazy. And so again, maybe it's doing things with them that practice those concepts, and something as simple as tables tests. Just fired off at the beginning of the lesson as a warm-up, as a starter activity. You say, right, okay, I'm just going to fire off tables at you. If that's what they're failing at, identify with your students where they're failing on making those silly mistakes, and also get them to understand that those silly mistakes will cost them large if they're not careful. Everybody starts with 100%, and every time they make a silly mistake, the level starts to drop, and they want to stop that dropping before it falls below the grade that they want. And what they need to understand is, 10 silly mistakes will take 10, 15, 20% of their mark. And the number of times my kids will go, oh, 7/8 of 56. Well, yes, you know that now, young man, but you didn't know it when you were doing the test. I can't give you the mark for it now because you didn't know it then. Oh, but I did. Yeah, but you're going too fast. So it's that notion of practice again, and so that they gain that procedural fluency, so that they see and know rather than have to work out some of those simple things.
All right, thank you, Michael. Thank you so much for facilitating this webinar. I hope you all found this a rich learning experience. Please make sure that you have clicked on the link and submitted all your details for the certificate. We will now end this session. Thank you for joining us.